Welcome back. In this last segment, as promised, I'm going to talk a little bit about quicksort. I'm just going to give you the intuition for it. We're not going to go through all the code, but you should actually know basically how it works. And again, it's going to be an n log n algorithm that works iteratively as opposed to recursively, so a little bit of savings in terms of the memory demands. All right, so same game. Let's take an array or a list with a bunch of elements in it. Again, let's make them unique. And our job is to sort them in increasing order. Let me specify 2 points, P and R, which is the beginning point and the end point. Let me start with 2 indices, I, which is -1 to begin with, and J, which is 0. So J is the element we're going to be looking at, and you'll see what I do with I in a minute. And let me define this very special thing called a pivot. The pivot is an element in the list. And there are a number of ways to pick the pivot, heuristically, to make this algorithm a little bit better. For now, we're just going to make it always the last element in the list. It's sort of arbitrary. You'll see what we're going to do with the pivot in a minute. So I'm going to pick the pivot to be the last element in the list. And my job now is to split this whole list into 2 sublists that are not sorted, not like merge sort, such that the first half has elements that are less than or equal to the pivot, and the second half of the list has elements that are greater than the pivot. And then you'll see what we do after that. So let's go ahead and do that first. So I look at the jth element and I ask, is this less than or equal to the pivot? The answer, of course, is yes. So I increment both I and j by 1. You'll see again what I'm going to use for I in a minute. So is this element greater than the pivot? Is it less than or equal to the pivot? No. So we move j over by 1, but we leave I here. So I is the point at which everything to the left is less than or equal to the pivot, and j is the moving front on this where we are analyzing everything. Okay? So is 7 less than or equal to the pivot? No. I stays put, j increments by 1. All right, what about 1? Sure it is. So now what we want to do is move 1 back to the I plus 1 position and move everything else over this way. So I'm going to take that's what's in this position right here, the 1, and I'm going to move it over to here, and I increment I by 1 because that's now everything to the left of the I's position is less than or equal to 4, and then everything to the right is greater than, except for j where we're still looking down the line. So same thing with 3, less than or equal to, sure. Move it over, increment I, increment j. 5, stay put, 6, stay put, and then 4, move it over. So at this point, notice where we are. The left half of the list is not sorted, 2, 1, 3, 4. The right half is not sorted, 7, 5, 6, 8. But it's not unsorted. That is, these elements are all less than or equal to the pivot, and these elements are all greater than the pivot. Now, how much time did that take to do that? Well, it was linear, right? I just walked through the list. Nothing very complicated. Did a comparison against the pivot, and then moved something over. So that's linear. So this splitting, like merge, is linear. And now, what do? Well, this sublist is almost sorted, and this sublist is almost sorted. So we're going to do it recursively, if you will, but not actually with a recursive call. So I'm going to take this sublist, and I'm going to do the same thing. I'm going to define a pivot. I'm going to move everything to the left that's less than or equal to it, everything to the right that's greater than or equal to it, and I'm going to repeat, 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 repeat. And so eventually what will happen is we keep breaking down until everything is fully sorted. And there are, of course, log n of that because I'm breaking the sublists in half each time. Okay? Now, one of the really nice things about Python is you don't actually have to implement this. It is given to you for free. So here's how you do after all of these lectures. Selection sort, insertion sort, merge sort, and what we just did in quicksort. The way you sort in Python is you're given a list, and you simply say L.sort. Notice that you don't say L equals L.sort. L.sort modifies the list that you are passing in, and so you simply call it, and this implements quicksort. It is, although there are lots of n log n runtime complexity sorting algorithms, quicksort is practically very, very fast when it comes to optimizing for various things that make it a little bit faster than some of the other n log n. So it is the go-to sorting algorithm that you will find built into many programming languages. Okay, that's it for sorting. We went through 4 sorting algorithms. There are dozens and dozens and dozens of them. You can keep reading about them all day long. varying degrees of complexity in terms of runtime complexity, but nothing better than n log n. N log n is a lower bound. There is no known sorting algorithm that works better than n log n. Lots of ones that are worse, n squared and worse. And quicksort is the go-to algorithm for sorting because practically when you go to implement it, it's very, very efficient. Okay, along the way, we did a lot of runtime analysis. And that's going to be the theme now from now on. We're going to be looking at different algorithms, different data structures. We're going to be looking at where you use them, how you use them, why you use them, and then looking at their efficiency and always going back and forth and comparing, what are the choices you want to make when you have to make decisions about data structures and algorithms. All right, that's it for this and for this lecture, and we'll pick it up in a little bit when we come back. See you soon.